Hello, everyone. We're excited to be kicking off the Objective by the Sea here with our talk in the realm of Rust. So we know a lot of people read our original write-up on the RustBucket malware earlier this year, but today we wanted to kind of recap on it and also dive into some of the details that we discovered maybe after the blog. But more importantly, we wanted to tell the story of the path we took really during this discovery and just how we went about hunting this in general. So my name is Jaron. I am here presenting with my good friend Sal. We both work at Jamf on the Threat Labs team, finding new ways to keep our customers safe from threats on the macOS platform.
So we have a number of seemingly different moving topics we'll be discussing today, including the release of a new analysis tool, as well as how we can craft our own C2 server to task the malware and better understand the attacker's objectives.
So before we get into the details of the malware itself, we wanted to briefly discuss the attackers that are behind it. So honestly, the best recap on what this threat actor group has been up to the past few years, to get the best recap, I'd highly recommend listening to the BBC podcast titled The Lazarus Heist. It's some quality in the car listening material. Long story short, Lazarus Group is suspected to be the North Korean state-sponsored hacking group. So when it comes to the macOS platform, we actually suspect they're one of the most active threats out there.
So real quick, let's highlight some of the campaigns from Lazarus. The 2014 Sony Pictures compromise has been attributed to Lazarus, where various internal documents containing sensitive information and data of Sony employees and senior executives were leaked. Later in 2017, the notorious WannaCry ransomware worm that impacted thousands of organizations across the globe has also been attributed to Lazarus. There have been two major supply chain attacks where we've seen earlier this year. The 3CX, a VoIP application used by millions of users around the world, was targeted in a supply chain attack that compromised several builds of their application on macOS. This led to a malicious dialib being dynamically loaded, distributed within the 3CX app. Although this attack was detected early, it could have had catastrophic impact for many organizations and users. Later this year, we've seen another supply chain attack compromising JumpCloud, an identity provider, and in a detailed report by Mandiant, they claim initial access was gained by targeting a JumpCloud employee and deploying malware to insert malicious code into their commands framework. The threat actor later deployed additional backdoors, established persistence, all within 24 hours of compromising the JumpCloud environment. So Lazarus aims to steal sensitive information from organizations to benefit the North Korean regime. Other times, they may have political motivation to conduct destructive attacks, such as denial of service against the South Korean government. With their vast range of tooling, resources, and targets, they have become a serious threat on macOS. Some intel companies attribute all activity from North Korea as Lazarus Group, and others break Lazarus Group into multiple subgroups. For example, BlueNoroff APT 38, or Stardust Chalima, first discovered in 2017 by Kaspersky, is considered to be a smaller specialized unit within the larger Lazarus Group that focuses primarily on financial gain. They are a financially motivated threat actor that has a goal of perpetrating financial institutions to steal funds that will later be used to further improve the North Korean political objectives. So the BlueNoroff subgroup campaigns included sophisticated bank heists, attacks on the SWIFT banking system. They've been linked to numerous attacks on banks worldwide, resulting in the thefts of millions of dollars. More recently, we've seen BlueNoroff target cryptocurrency companies and venture capital firms. Kaspersky researched similar attacks on the Windows side as well.
So the way that Lazarus is getting their foot in the door to these networks is by building rapport with their victims primarily. So they come into users' mailboxes asking smart questions, showing interest in purchasing the company, investing, whatever it be, or maybe just partnering in some way, which naturally many of these small crypto startups kind of have a lot of interest in doing, and they get a lot of response back from who they're reaching out to because they're very targeted in who they're choosing. So ESET did a really good write-up on one of these campaigns that involved this technique. The campaign was titled Operation Dream Job. In this campaign, they would reach out offering victims potential jobs. at a company like Coinbase, for example, and then at some point, they would convince the user to run an app, which would ultimately end up displaying a PDF document. We don't know exactly how or what the chain was for that, but we know that they'd ultimately get this kind of job opportunity in front of them by the end. Meanwhile, while opening this, they would actually be executing something in the background that they had no idea was occurring.
So like we stated, we wanted to share the journey we went on to unveil RustBucket. We didn't discover this malware running on a customer device. We actually found it on VirusTotal and had to go hunting for all the moving pieces, as we'll get into shortly. But for now, let's just focus on what put us on this wild goose chase in the first place. What's funny is we were not actually in search of new malware families at all. We were just performing some routine searches for new possible variants of the XCS set malware. And one way we go about doing this is performing some searches for the curl command running from within compiled AppleScript. We do this by crafting a search that first looks for an AppleScript header, and then looks for the curl command existing somewhere inside the executable. This is a very, very generic search, but it served us well in the past. So on a random day, we decided to take a look for malware using this technique. And instead of finding a variation of the XCS set malware, we encountered something entirely different. As expected, it was a compiled AppleScript that was utilizing curl in order to download a second stage payload, but it looked far too simplistic to be XCS set malware. We took this resulting AppleScript and saw that it was uploaded to VirusTotal as part of a zip submission. We grabbed the zip and of course discovered that the AppleScript was the main payload of a larger compiled AppleScript application. This greater application was called Internal PDF Viewer. It was completely unsigned and unnotarized, so we had an unsigned compiled AppleScript that contained a curl command within it, and not only that, but it was a pretty generic social engineering-like name. So all these signs combined justified further investigation for us.
All right, so let's put a pin in that for just a second. We're going to come back to that because right now we wanted to quickly introduce a tool that we're going to release that we can use to dynamically analyze this sample that we've now found. But we'll do that with some example data first. And that's a major project that I've had under development for a long period of time titled SpriteTree. So as many of you know, I've long preached about hunting malicious activity using process tree-based data, which is difficult to present correctly on macOS. For this purpose, a few years ago at this very conference, I released a tool called TrueTree that tries to generate this PS tree-like output on macOS. So I've long had the desire to basically take TrueTree, take it a step further, and kind of build a tool that allows you to do this with ES data from over a short capture. So today at the mittenmac.com, you can download this new tool titled SpriteTree. So I did not and could not have done this alone. This project I built with two good friends of mine, Maggie Zernhelt and Matt Schott, both who are here today as well. So we spent a lot of our free time trying to put together a really cool tool that takes ESLogger data and visually displays it for malware analysis or system internals investigation. So that's how we came up with SpriteTree. So with SpriteTree, you can do an ESLogger capture, you can load it in, and what you're looking at here is the application, which is written purely in Swift. Swift UI uses Apple's SpriteKit game builder framework to display data. You might ask why we went about it this way and wrote it from scratch in Swift when there's a lot of visualization frameworks out there. Well, ultimately, a lot of those are written, D3. There's a lot of JavaScript for that. We wanted to do something that was native and allows us to expand this tool in the future and basically come up with new ways to kind of present that data to users. So that's why we opted to go this route with it. So a bit on how it works. First off, its primary purpose is to take data captured from Apple's ESLogger tool. So this command line tool got added in Ventura, so on any system running Ventura, you can run a command, a command that looks something like this, where you see we're calling ESLogger to start a capture. We're telling it to look for the fork, exec, create, and rename events. So we can capture these in any order. These are the current events that we support for SpriteTree. We'll add more in the future as well. Finally, we'll redirect the results to just a temporary JSON file that we'll be able to load into SpriteTree later on. So now we're recording events on the operating system, and we'll start, generating some user activity. I'm not gonna make you watch everything I'm typing in here, but just know that we punch in a handful of commands, and now we can come over to SpriteTree, and we can load that data in. So you're immediately greeted with this process tree that looks for the events that took place. Now, by default, the tree is going to be displayed using parent process ID and PID, which does not, as mentioned, give us the best context into what happened on the system. So, for example, over here, you can see we just have a terminal process that's hanging out by itself. We know terminal probably went on to do stuff, but based on the way that macOS captures forks and execs in real time, this is what a standard tree would end up looking like. So by pressing escape within our tool, you can open a menu that allows us to select a PID to build this process tree by. So we're going to use the true tree format here, and that's going to take a lot of the forks and the execs. It's going to organize them in a way that makes more sense. It will also resort to the responsible PID and the original parent process ID when building the process tree before it decides to give up and just opt to the parent PID if it can't find anything else. So overall, this should clean up the capture, makes sense a lot more visually, and you can see this builds a much more helpful and cleaner process tree for us to analyze. So one of the first things you'll notice when you open this tool is that some of the nodes have this smoky effect. That's just to represent the forks that occurred, and the rest are execs. If you look at the process tree, you'll notice we're looking at a branch for the terminal we opened. First is a list of commands that kind of get executed in the background when you open a terminal. And then we see a handful of commands that I executed as a user, right? Because we were capturing these in real time. We'll go ahead and click on the ping node. We see we get a nice highlighted path that follows up the tree. If you're dealing with a very large capture, it's nicer on the eyes to just kind of highlight what's going where. Secondly, we get a button up top that allows us to open the details of this node. So if we want to see the raw JSON that came through with this event, we can click on that, and now we can see it. Here you can see the arguments, that we executed it with. We get the raw PIDs, we get the values. We have changed the format of the app ever so slightly so that it's not just raw JSON sitting there. It's nice fields instead. But you'll notice the app has been updated a little bit since I took this recording. But yeah, it's the same idea. So as an analyst, you spend a lot of time performing these same actions, looking for commands that are run, selecting processes, looking around in JSON, and now we just wanted to bring that into a nice little compact tool. So that's a quick crash course on moving around the tree and browsing data. Now we do have a few other bonus features with this app. So for example, you may have noticed in the settings menu earlier, we do also have the option to color the tree by two different PIDs, one being process group ID, as well as the responsible PID. So this is helpful because it allows us to build the tree using a more logical tree layout while then coloring the nodes based on their responsible process. So think of this as a way to visualize the processes that share macOS permissions. For example, here you can see that all processes that were under the terminal are this salmon kind of color. So although terminal has two large branches of commands open, we can see that they all share the same responsible process, and therefore every command run in this terminal is operating with the same TCC permissions, presumably. So in other words, if the terminal application has full disk access, so does everything under it in this case. Any way to get around this would kind of be considered an exploit. For example, a few years back, we see for example, here you see the SSH command run. A few years back, there was a piece of malware that would log into the local host using SSH. It did this because when you log in over SSH, even if you log into your own local host, you're actually generating a completely different tree under the SSH daemon, resulting in a new set of active permissions. So we can kind of see here, because the color changes, we know and we have code execution under SSH now, that we know the permissions SSH is operating with are different. So this means that whatever commands we run with the TCC permissions of SSH agent rather than the terminal now. So malware could easily gain full disk access by logging into the local host of the computer over SSH. But Apple has patched this by now making a tick box when you enable remote login that has to be done through user settings. So that was a very quick crash course on SpriteTree. I will release a blog post with some technical details of how it works and what all the PIDs are. But right now we wanted to get a tool out at this conference that you could play with and just get it in your hands so you can analyze some different events in kind of this fun manner. But let's go back to where we left off and start looking at RustBucket inside of SpriteTree. So we take this RustBucket sample, we launch it, we record, and we start seeing what actually happens, right? And so we're kind of using it in this short kind of sandbox capture mode for analysis. This is laid out in true tree mode. Really, there's only one branch of activity here that jumps out pretty quick in terms of what happened. For those that are familiar with AppleScript, you probably know that when you compile your AppleScript into an application, the executable name with the application is simply named Applet. And that's what we kind of see here. We see something with the name Applet ran, but further up we see that it has the actual app name of internal PDF viewer.app. So let's keep looking. Returning to the process tree, we see that 3 different child processes were created. By the way, another quick note, any nodes that kind of have a blinking node within them means there's a context-related event. So I know that one of these nodes performed a create or a file rename or something like that. So let's take a look at the curl command that executed under RustBucket, and we see that there's a curl out to an attacker C2, where it looks like what it's pulling down is something called 1.zip. And we can confirm that this was successful by clicking on the context tab, and we see that 1.zip was in fact created by this node. So if we go back to our process tree and we see that the app then executes the unzip command, this is of course going to mean we should get a bunch of file create events where we see this 1zip file seems to be holding yet another application called internal PDF reader. Still pretty weird. Internal PDF reader curled out somewhere to pull down another internal PDF reader. Finally, we have the last command, which runs the open command. We probably know what's going to happen here, right? Open is going to then go open this newly downloaded app. So the stage 1 is actually very simplistic, and just by looking at the output in SpriteTree, we kind of know, we can kind of conclude how this app really works. Basically, someone created an AppleScript file with only 3 commands in it, the 3 commands that we saw then get executed. When then OSA compile gets used to turn AppleScript into a compiled application called internal PDF viewer. This is the stage 1 malware, and ultimately what gets sent to the victim, which is then executed and runs and downloads another PDF reader. So the question still remains, what does internal PDF reader then do? Well, in here we can see that it does nothing. In fact, we see that when the application opened, no further commands were performed, at least from a bash perspective. And the only thing the user sees is this junky-looking PDF tool, which will in fact legitimately load a PDF if you're in the market for a new viewer. Knowing that something suspicious was going on, we obviously loaded this up in a decompiler, and the code, as you might expect, is fairly minimal, but we did encounter a function that we took great interest in called down and execute. A function that was not triggering when we opened it. We didn't know why, but now based on some of the other assembly, we suspected that if the correct PDF was opened, this function would get called. So really making the correct PDF kind of like a key to trigger the rest of the malware. So we couldn't get it to execute, but and we did a bunch of playing around, and it was kind of hard. The malware is very cryptic, did a lot of XOR encoding. We did notice something inside the macOS, which was a large set of bytes we suspected could be an XOR key. So after exhausting a lot of our options and staring at decompilers for too long, we decided to go back to VT again. And this time the bytes we were going to search for were a little different. We were going to search for PDF file where the XOR key that we saw in the app we wanted to find in the PDF. And really, this time, we ended up finding 3 items. And this was kind of a Hail Mary, right? There's no real reason for us to be doing this, but we thought, hey, maybe. So we got a handful of PDFs, all kind of interesting names, maybe possibly also related to some social engineering campaigns of some type. So we grabbed the documents and decided to blindly throw them into the PDF reader, because why not? You can see that when we open the file, we get a heads up that this file requires special software to view the data. But when we open it inside the app, when we open the PDF inside the malicious app, it actually decodes to be a document that you can actually read. So we know it's all a front, and we know this because running this actually did get our down and execute function to work. However, there was one problem. Inside the NSURL session that we were expecting to find a URL, we found something very, very much blah instead that didn't decrypt anything. However, it looks like it could be about the length of a URL, right? So this was probably a PDF used, but it was not the PDF we were looking for. So we decided to throw up one last Hail Mary. We take the bytes of HTTPS, and we XOR them with the XOR key that we found in the malware, and we, of course, get a new set of bytes. We return to a very familiar query back to VirusTotal, where we're doing a search for PDF files with this new set of bytes, hoping we find something. And in this case, we found a single file on VirusTotal that came back, a PDF file titled investment strategy protected.pdf. So, sure enough, we load this in the file. We load this file, and the URL is decoded. And we decided the first set of files we found were probably either for a Windows variant or an old variant that put the XOR key in the PDF rather than expecting it to be in the application already. So now the XOR was embedded within the application, so it having to be in the PDF was no longer required. So if we go back to SpriteTree, we can see that our stage 2 internal PDF viewer does have some context events. Since it's an application, it's almost guaranteed to have some type of kind of temporary files that get used for, stored states that applications use. So there is some generic stuff in there that's not super interesting. But we do see that there are 2 easy to overlook events. One where a temp file gets created, and that file immediately gets renamed. So the file name gets renamed to actually just get set to whatever the current mock timestamp is on the system. So a cool feature in SpriteTree that I've saved for last is that we've added a timeline slider. So what you're looking at here are the processes that exist before the correct PDF was loaded into the stage 2. If we drag that timeline slider, we see what happens after the correct PDF is loaded into the app. We see here that the file that was written and renamed was then executed to perform a number of different actions. But right when it executes, it seems to run some recon commands. This we determined, this executable is the official 3rd stage malware. So really quick, we had mentioned earlier that this application was not signed at all. You might be wondering how the attackers were getting around Gatekeeper. Keep in mind that they have built rapport with their victim, likely over LinkedIn or email. So the way they're getting victims to execute this is by providing instructions on how to override Gatekeeper. In other words, in this kind of broken English, how to right-click and then click open. We know this is what the attacker was doing because, again, in the in an ESET finding released after our blog post, they showed they had discovered zip files that kind of included a PDF, the PDF reader, and then a README on how to override Gatekeeper to get the app to open. So that's a lot of information about our journey through the stage 2. Sal's now going to talk about our journey through the stage 3 malware, which we quickly discovered was written in Rust.
Thank you. So in this section, I'll begin to cover some background on Rust, including some of the challenges with reversing Rust binaries on macOS. Following this, we'll begin to analyze the stage 3 component of this malware, and after understanding the structure of the command and control tasking, we will build our own C2 server to communicate with it. This will help solidify our understanding of how the malware operates. Rust is an intriguing language conceived in 2010 as a brainchild of Mozilla Research. What sets Rust apart is its meticulous design to combat prevalent programming pitfalls. It inherently mitigates memory errors, offering a safer programming environment that reduces risks such as null pointer dereferences and buffer overflows. With this package manager Cargo, Rust boasts rapidly of an expanding ecosystem, making it easier for developers to integrate libraries and tools. There are 3 different known macOS malware families written in Rust. Realist is an info stealer that is capable of stealing crypto wallets, stored passwords, and various browser data. Its campaigns involve the distribution of fake blockchain games, including targeting victims on social media platforms. Then following Crate Depression is the name of a campaign that involved a supply chain attack leveraging a malicious crate. After identifying the victim's platform, it downloads the Mythic Poseidon payload, a well-known exploitation framework. Finally, Convustor is an adware family written in Rust, and it has limited functionality, but it does obtain the device ID as well as system version and forwards it to the C2. Before we dive into the 3rd stage component of the RustBucket malware, it's important to discuss some of the challenges with reversing Rust compiled binaries on macOS and how we can overcome them. Although there are many benefits developing in Rust, this also means malware authors can benefit in writing their malware in Rust. By default, Rust statically links its standard libraries into the binary. That essentially means that all the necessary runtime code and dependencies are included in the binary itself. This also introduces some challenges for reverse engineers dealing with substantially larger binaries. The program entry point is a short basic block that does not actually call the program's actual main function directly. Instead, it provides the main function as a parameter to another function called langstart. Name mangling is a technique used by compilers to generate unique names for programming entities that might otherwise have the same name. This ensures that the resulting binary can correctly link different entities without name collisions. Rust, like C++ and some other languages, uses name mangling for these reasons. For reverse engineers, these mangled names can be a hurdle because they make the binary harder to understand. Rust actually provides a crate specifically for demangling Rust symbols, Rust C-demangle, and allows you to programmatically demangle Rust symbols within a Rust program as well. There's also third-party crates that perform this action as well, such as rustfilt. Identifying crates can give insights into the dependencies a program uses, and knowing these dependencies can help in understanding the program's functionality. So as we go through our analysis, we will identify various Rust crates that the malware is using here, and this will help us identify a timeline as to when the malware may have been developed. So now let's dive into the 3rd stage component of the malware. A quick triage indicates that this is a Rust-compiled executable, and it's a universal binary that is ad hoc signed. So there's a number of indications that will tell us that this is a Rust-compiled binary. By looking at the mangled scheme, standard library symbols that Rust uses, and unique compiler metadata, Rust uses its own compiler, rustc, and the rustc compiler is developed by the Rust project, and it's responsible for translating code into executable binaries. So as previously mentioned, Rust uses a package manager called Cargo, and Cargo handles project building, dependency management, and also provides a central repo for sharing Rust libraries and applications. And this repository is known as crates.io. So looking for strings within the binary containing Cargo or rustc is a good indication that this is a Rust-compiled executable. So when the stage 2 malware executes to stage 3, it passes the C2 URL as an argument to it. This is actually required for the stage 3 malware to communicate with the attacker server. At the program entry point, we have a call to a unique crate called webT. This webT crate is actually not a known crate, and it doesn't exist on the crates.io repository, indicating some custom code is being developed. It calls the langstart and passes the main function as a parameter to it, beginning the execution. Following this, the J instruction, or jump if above, checks the result of the preceding compare instruction and will jump to the appropriate address if the value in RBX is greater than but not equal to 1. So the malware will self-terminate if its C2 URL is not provided as an argument. The very first thing the malware does is generate a random 16-byte value using the rand crate. This unique random value will be used to identify the victims that are checking into the C2. Note here that we've demangled the function calls from our decompiler output to easily read the functions that are being called, and we'll do this as we go through the analysis. The malware proceeds to call a function called get_comname from the WebT crate to gather the computer name. It does this by using a crate titled getHostname. The malware proceeds to call a function called get_osinfo within the same getinfo namespace to acquire the operating system version it is running on. It then invokes the OS type crate to call a function called current_platform. The crate goes on to run the sw_version command to determine the version of the software it's running on. Interesting enough, this OS type crate fails to fetch the correct OS version information and defaults to 0.0.0 as indicated in the documentation. The malware then gathers the installation timestamp by calling the getInstallTime function within the getinfo namespace. This essentially runs stat on var log install.log to get the file's creation time. It's going to be used as an indicator for the installation timestamp on macOS, meaning if you're spinning up a VM to do malware analysis, the installation timestamp will be really recent and may be used as an indicator to determine the legitimacy of the system. The malware also gathers the boot timestamp by calling the getBootTime function within the getinfo namespace. This function uses a sysinfo crate to call boot time and get the system boot time. The malware then gathers the current timestamp, calling the function getCurrentTime from within the WebT crate. It uses the chrono crate to determine the current timestamp. The malware determines if it's within a VM by executing a shell command using the subprocess crate. It does this by shelling out to the system profiler command sp hardware data type, grepping for the model name and model identifier. The malware then calls the function get_processlist within the WebT crate to gather running processes. This is important information for the attacker to determine the environment that it is in. Presumably, if it's a target of interest, it may deploy additional backdoors or payloads and get around security tools that may be running on the system. As we already mentioned, BlueNoroff is interested in obtaining financial assets. Following this, the malware does a string-to-byte conversion and sends the data to the C2, calling the sendRequest function within the WebT crate. The malware begins to craft a post request to send to the C2 containing all the collected data as gathered up to this point. It does this using the request crate. The request crate is a popular HTTP client library used in Rust for sending data using HTTP requests. The malware then sleeps for 60 seconds before it can receive any further instructions from the C2. So after identifying various Rust crates the malware is using, we can actually leverage this information to try and determine when the third stage RustBucket backdoor was developed. Using the specific versioning information from the crates we identified in the malware, we can compare that with the crates.io version control timestamps to develop a timeline as to when the malware was likely developed. With the assumption that the malware author was using the latest available version of the crate at the time of development, we can deduce that the malware was likely developed between October of 2022 and December of 2022. This also lines up with the fact that the earliest RustBucket samples we've seen on VirusTotal were in 2023. Getting back to our analysis, there's some hidden functionality within this malware. If it receives a response from the server to check to see if the response value is hex 31 or 1 in ASCII. In such a case, the malware will actually self-terminate. If the response it receives from the server is hex 30 or 0 in ASCII, the malware will download and execute the payload received from the server in the CS Darwin user temp directory. Let's take a closer look into the command structure of the download event. As mentioned, the hex value 30 indicates a download event. This is followed by the hex value 23, which is used as a separator. And any command line arguments are specified following this. Next, we have a null byte followed by another separator using the hex value 3a. And finally, our payload bytes to download and execute will follow. This can be any macOS, binary, script, or shell command. So to recap, the malware generates a 16-byte random value to uniquely identify the victim. It gathers the host name, OS version, install, boot, and current timestamps, checks to see if it's within a VM by running the system profiler command, and finally gathering all of the running processes on the system. It sleeps for 60 seconds, awaits a response from the server to perform further actions. If no response is received, the malware will actually continue to go through this entire process again. So if the server contains PW as its post data, this is an indication that the victim has ran the stage 2 malware. The server will then download the stage 3 component of the malware, which is the Rust binary that we're analyzing here. If the server receives CI as its post data, which likely means a check-in is occurring, it will log all of the post data. This is the various information such as timestamps, process information are all being logged on the server side. A custom response is then served depending on what action the server would select to do, in downloading additional payloads, executing shell commands, or sending a signal to terminate the malware. If the server decides to execute a payload on the victim system, it will send a custom response to the post request check-in. This custom response will contain the payload to be executed along with the appropriate bytes prepended to it so the client can process it. After it's finished executing the payload, the client will then send another post request with the CS, or command status, followed by the 16-byte random value and a 0 or 1 indicating the status of the payload that executed. If the server decides to terminate or kill the malware, it will send the hex value 31 as a response to the post request. The malware will then send another post request with the CS value, followed by a random 16-byte value to identify the victim, and -1 indicating the malware was successfully terminated. If you're inspecting packets at the network layer, this may be great indicators to monitor and block C2 traffic based on the post data that we just discussed. Knowing all of this information, we can build our own C2 server in Rust to communicate with the RustBucket backdoor. To do this, we need to process HTTP requests, serve custom HTTP responses, task the malware to download payloads or self-terminate, and finally log all of the relevant check-in information on the server. So here we begin to initiate a TCP server that binds to port 80, allowing it to listen for incoming HTTP requests. It can also filter these requests based on the user agent that's being supplied. For every incoming connection, our server spawns a new thread to handle the client's requests. This allows the server to manage multiple connections concurrently. The server parses the HTTP requests to determine the type of requests. If it's a post request, further checks are performed to identify specific actions or tasks to be executed. The server is specifically designed to handle post requests, but not all post requests are treated the same. The server inspects the beginning of the post data, as we mentioned, to determine the appropriate action. If the post data begins with PW, the server will serve the stage 3 Rust payload, indication that someone ran the stage 2 binary. If the post data begins with CI, server or check-in, the server will log the post data and prompts to serve a custom response. This custom response can be used to terminate the malware or execute additional payloads. Finally, if the post data begins with CS, command status, it will print the appropriate status message to determine if the command was successfully executed or not. The server has predefined byte sequences, execute response bytes, and terminate response bytes, and it can be prefixed to some of the responses. The execute response bytes, these are sequences of bytes as an instruction or a signal for the client to execute subsequent scripts or binaries, and then terminate response bytes will terminate or kill the signal, will send a kill signal to the client. Let's take a look at the perspective of the victim running the malware. They have a PDF file that they receive indicating that they must open it with this dedicated PDF viewer application. You can see here that the PDF matches the same version of the PDF viewer application. Upon opening the PDF file in the PDF viewer or using preview on macOS, it only displays a single page, but when using this malicious internal PDF viewer, the PDF document is open and immediately displays a different PDF that is much larger. And using Lulu, we can see the network communication to our own C2 server. At this point, our server has already served the stage 3 payload. It has executed and gathered various information from the victim as well. From our custom C2, we can task the malware to download and execute payloads. For demonstration purposes, we just simply launched Calculator to illustrate its functionality. Now let's take a look at the server side and the relevant data we get back. Immediately, we see that the post request check-in, including the post data, including the post data that the victim has sent. This information is logged on our server. We can then decide on the customer response to send the malware. This is where we opt to launch Calculator on the client system. We also get back the response from the client indicating the payload was successfully executed. Awaiting the next check-in, we then task the malware to self-terminate. And we get the CS response followed by the 16-byte random value and the -1 at the end of it, which tells us the malware terminated successfully. So we can confirm our analysis by checking the log file to see the data we received from the RustBucket Stage 3 client. It is clear here the malware is very selective in who it targets and surveys its environment very closely before deploying additional payloads. This is also an indication that the malware authors are willing to adapt and leverage new programming languages such as Rust to allow for more efficient and performant malware while also inherently introducing some challenges for reverse engineers. Elastic Security Labs also discovered a persistent variant of the RustBucket malware, and which they detailed in their blog. So definitely check that out if you're interested in more RustBucket analysis.
So that wraps up our talk and our journey kind of through the RustBucket malware. We wanted to give a quick shout out to Sungsu from Kaspersky and Greg at Proofpoint, as well as Arnaud, aka Nor from Space, for collaborating with us on some of the intel and just working with some details back and forth that we really appreciated. SpriteTree can be downloaded from my website, themittenmac.com. You can generate and import your own captures, but if you want to, we've included some captures of RustBucket, along with some of the other captures that you can load in as well. I apologize that we are notorious for not leaving time for questions, but if you have any, please reach out on Discord, or feel free to catch us at some point later today. So thank you very much, and looking forward to the upcoming talks.
Excited about the new tool.